This is Algebra 2 at Trig, Unit 9.4. We're going to talk about probabilities of disjoint, also known as mutually exclusive. When you consider all the outcomes of either of the two events, A and B, you are forming a union. So this is an example of a union. All the events of A and all the events of B, it's a union. It's grouping them together. That's A and B. When you consider only the outcomes shared by A and B, you have the intersection. Here would be the intersection. That's where they're shared in A and B. So the union or the intersection is called a compound. These are compound events. So to find the probability of A or B, you must consider what outcomes, if any, are on the intersection. So we're looking for overlapping. So in this case, we have some that are overlapping. But in this case, we do not have any overlapping. You could call this mutually exclusive. They are completely separate from each other. They do not overlap at all. Also known as disjoint. They are not connected. These are connected, and this is where they're connected. So two events are disjoint or mutually exclusive if they have no outcomes in common, which is our third diagram. So that's what we've done up to this point. When it's been A or B, we've added the probability of A and the probability of B. So if A and B are two events, then the probability of A or B is the probability of A plus the probability of B. That's what we've done in the past. But now we have to worry about the probability of A and B. We have to subtract the numbers that we've counted twice. If you count all the numbers in A, all the dots in A, and you count all the dots in B, you have to subtract the ones that you've counted twice. In the past, we've been working on situations that were disjoint. Like the deck of cards. You couldn't have one card that was actually another card. Okay, so we were doing with disjoint situations, and that was just the probability of A plus the probability of B. So you have to pay attention to the situation that you're dealing with. You have to get invested in the question to understand what's being asked. You don't just answer it. You got to understand the question. So you roll a 6-sided cube. What's the probability of rolling a 2 or a 5? You're going to win if you roll a 2 or a 5. So what's the probability? Well, you know that event A, which is rolling a 2, and event B, which is rolling a 5. Event A has one way to do that, has one outcome. B, rolling a 5, has one outcome. Because events A and B are mutually exclusive, because they can't roll a 2 that is a 5, we know the probability of A or B is the probability of A plus the probability of B. You're one or the other. So that's 1 out of 6 plus 1 out of 6, which is 2 out of 6, which can be reduced. That's a 1 out of 3. Notice we don't write our answers as a percent. Always write our numbers between 0 and 1. So now we're down here. A card is randomly selected from a deck of 52. What's the probability that it is a face card or a spade? So if we look at all the face cards, if you look at our Venn diagram here, you have a face card. There are 12 of them. You could have looked at your chart and noticed that there were 12 face cards. These are the 12 face cards. And event B were all the spades. And if you look here, you have all the spades. So there's 13 spades here. There are 12 face cards here. So you can notice that you're going to overlap. If you count the 12 face cards and if you count the 13 spades, you overlapped. You counted some of them twice. So the probability of a face card or a spade is going to be the probability of a face card, which is 12 out of 52, plus the probability of a spade, which is 13 out of 52, minus the probability of the face cards that are spades, a face card and a spade. And we saw that there were 3 of them. So that gives us 22 out of 52, which can be reduced. Questions about that? Okay, on the flip side. So we have our formula that says the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That's in situations where they overlap. That's not in every situation. There are some situations that A and B are completely separate. They can't overlap. But we talked about the cards where they do overlap. A number of 100 students is surveyed. 92 of those 100 have a car or a computer. 65 of them have a car. 82 of them have a computer. What we want to know is what's the probability that a student is selected owns a car and a computer. So we're going to use our formula. So the probability of a car or a computer is going to equal the probability of a car plus the probability of a computer minus the probability of a car and a computer. So that's just using the formula right across the top. The one we talked about on the front side. So we saw that 92 out of 100 have either a car or a computer. So that goes into 92 out of 100. 65 own a car, 82 own a computer, and mathematically we can now use algebra to determine this variable. It could have been whichever one they wanted to leave blank. You saw for the unknown. This happens to be our unknown. So what we're going to do is collect these together. So that's 147. So we're just doing an algebra problem. We subtract this across. So when you subtract it across, you get negative 55 over 100 is going to equal the probability of a car and a computer. And, oh, I'm sorry, the negative has to be there. The minus. Right? When you add those two together, it still has a minus the probability. And then when you subtract the 147, you still have the minus the probability. So now we're going to divide that out. So that's the probability of a car and a computer. 55 out of 100. We solved for the missing part. We'll practice that some more at the end. We have complement events. Complement events is everything that is not A. This has a bar over it. You got to look carefully. You'll see that this is a bar, and that's read as not A. That's considered the complement. The complement is everything else. So the probability of a complement of A, which is known as everything that is not A, is 1 minus the probability that it is A. So what's the probability that you draw a 7? Or I'm sorry, do not draw a 7. What's the probability you do not draw a 7? Now, I bet naturally most of you are going to do this automatically. You're going to naturally do this practice right there. I doubt the majority of you are going to come in here and add the kings up. There's 4 of them. Add the queens up. There's 4 of them. The jacks, the 10s, the 9s, the 8s. Skip the 7s because those are the ones we're talking about. 6s, 5, 4, 3, 2, and aces. You're not going to add all those up. Maybe somebody would, but if you're going to try to find the probability of not a 7, it would be a little bit faster to say 1 minus the probability it was a 7, which is 1 minus 4 out of 52. Well, that would be 52 out of 52 minus 4 out of 52, which is 48 out of 52, which can be reduced. 12 out of 13. There are 12 in every suit that are not 7s, and that's true for every suit. So it reduces to 12 out of 13. The card is not a red face card. Not a red face card. The king of clubs is not, or king of spades. King of spades is not a red face card. King of clubs is not a red face card. Queen of spades is not a red face card. And you can go all the way through there. And you can count any card that is not a red face card. That would be one way to do it. Somewhat reasonable because the number is not infinite. Or it's not a whole bunch. It's only 52 cards to worry about. But naturally, many of you are going to say the probability of not a red face card is going to be 1 minus the probability of a red face card, which is 52 out of 52. We talked about that's the value of 1, minus the 6 cards that are red face cards. So that's going to give us 46 out of 52. And you can reduce that. 23 out of 26. Okay, here's kind of a complicated one. Listen to this one. There are 10 people at a dinner party, or 10 people that walk into the class, or 10 people somewhere. What is the probability that at least 2 have the same birthday? Okay, that somebody in there shares a birthday with another. That's what they're asking. So you would have to find the probability of 2, then you have to find the probability of 3, then 4, then 5, then 6, 7, 8, 9, and 10. That would be a lot of work. That would be pretty tough. But if you just work on it as the probability, which is 1 minus no common birthday, you can just find the probability that no one has the same birthday, and you've saved yourself all the other calculations of 2 or 3 or 4 or 5 and having to add those all together. So this is where the complement comes really in handy. It would be difficult to calculate all those others. This won't be too bad. So we know that 1 is going to be, it has to have common denominators. So since your birthday can be any of the 365, 1 is going to be represented by 365 divided by 365. And we're going to subtract that by the probability that no one has the same birthday. How many days can the first person that's surveyed have their birthday in? Can the first person get matched with anybody if they haven't, if we have nobody to match it with? The first person that walks into the room can't have the same birth date as anybody else because they're the first person. So that's 365 over 365. But the second person has to have a different birthday. So we're going to say that they have 364 days that their birthday could land in. The third person has to have a different birthday. And we would continue that pattern all the way down. I believe it is 356. Goes down to 356 over 365. So we could do it in that format, but that would be, still, that's a lot of buttons to push. 10 different values have to be in there. So the shortcut to write that is 1 minus 365p10 over 365 to the 10th power. That's the shortcut. That you'll appreciate. This is a probability that no one has the same number, birthday. So this becomes 1 minus 0.883, which is 0.1169. So there's an 88% chance nobody has the same birth date, which is going to turn into an 1169% chance that does not, or that they would have the same birthday. Phew, that's a crazy one. Okay, this is the first time I believe you've seen the dice. This is your chart for the dice. So notice how the dice work. We have two different colored dice. That's to show you that you're rolling two different die. So the first die could be a 1, the second die could be any number. The first die could have been a 2, the second die could have been any number. There are 36 possible ways to roll a die. "36 outcomes." That would be a better, rather than saying ways, 36 outcomes to roll the die. This would be those. You couldn't roll the die in any other pattern. Okay? They're all, the outcomes are there. So, when two 6-sided die are rolled, what's the probability that the sum is less than 10? Well, you could come over here and you could add together all the sums that are less than 10. 1 and 1 is less than 10. 1 and 2 is less than 10. So that's a sum of 3, sum of 4, sum of 5, sum of 6, sum of 7, sum of 8, sum of 9. You could add up all those different possibilities. I imagine some of you would do it that way. That's okay. That will work. But for you to start to understand how the complement works and to be ready to submit this for larger problems, you want to understand that you can also do all the possibilities minus the probability that it is a 10 or bigger. So this is 1 minus. To have a 10, there are 3 ways to have a 10. There are 2 ways to have an 11. And there's only 1 way to have a 12. So that's going to be 1 minus 11 out of 36. Which reduces to 25 over 36. Because you need common denominators. 36 over 36 minus the 11 gives you 25 over 36. Sorry, I cheated. That's not an 11. 3 plus 2 plus 1. 5 plus 1 is 6. There are 6. And that means there are 30 out of 36. And 6 goes into there 5 times, 6 goes into there 6 times. So 5/6. Thank you for pointing that out. You'll see where the other numbers come from. All right? What if the sum is not a 7 or an 8? We could come over here and look for a 7. That would be 1, 2, 3, 4, 5, 6. Or an 8. 1, 2, 3, 4, 5. So what we're going to do is 1 minus the probability of a 7 or an 8, which is 1 minus 6 over 36 plus 5 over 36. There's my 11. 1 minus 11 over 36. And that gives us our 25 over 36. And greater than 9 but less than 4. Can you have a number that is greater than and less than 9? probability of A plus the probability of B, A or B. We got two things going on, one or the other. That's the probability that you're less than 9 and the probability that you are greater than 4. There are 6 out of 36 that are less than 9. And there are, less than 4. Greater than 9. That's greater than 9. We've got 3 out of 36, which gives us 9 out of 36, which is 1/4. I feel I have these signs backwards. Man. All right. This would be greater than 9. The numbers making 9 smaller, and these would be the numbers making 4 larger. So you're less than 4, you are greater than 9. Okay, last set. Notice how they have the A, the B, the A or the B, and the A and the B. So we're going to use our formula of the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, what we did in the very beginning. The OR is what we're solving for. 0.6 is your A, 0.32 is your B, and minus 0.25 would be your overlap. So the probability of A or B is going to be 0.6 plus 0.32 minus 0.25. And that gives us 0.67. And then our last one over here, this is the probability of A or B equals the probability of A, probability of B, probability of A and B. OR is 0.5, A is 0.25, B is 0.4, and we're going to solve for the AND. So it's just an algebra problem. So we add those two together and we get 0.65. Subtract the 0.65. We should be getting a negative answer. And then you divide by the negative. Just an algebra problem.